So I want to do one more video about Bayes' theorem, and what I want to do now is to do a somewhat more complicated pedigree and make it add things to it one by one. And why I want to do this is so that we can practice seeing how we use Bayes' theorem to update our probabilities as we get more data. We do this all the time in the world. The more we learn about the world, the more times we go to a certain stoplight and see whether it's a long stoplight or a short stoplight. The more times we have a conversation with someone and learn more about them, we shift our hypotheses about the world. And Bayes is just the way that we do that in the context of explicit probability. So let's get into this. We're going to start with our pedigree that we've been using a lot of, where we have two heterozygotes and they have an offspring that is not affected, and we want to ask, is this individual a carrier? So we're going to start with the problem we've been doing, and then we're going to add more and more information. So in general, we said that what we're going to do is use Bayes' theorem to ask the probability that the individual is, the probability of B, which is the probability that the individual is a heterozygote, given A. And here A is going to be everything we know, so what our data is. Okay, so when we start out here with individual, so let's actually start before we know even the phenotype of this individual. So before we know the phenotype of this individual, right, before they're born, then what are B and A? Well, it's kind of weird here, because here we would say that, so B is the probability the individual is a heterozygote, and A is, what do we know? What do we know about this individual? Well, we know that their parents are heterozygotes, but we don't know anything else, right? So to start out with, before the phenotype, we would say, okay, so then the probability that the individual is heterozygous, given that they have heterozygous parents. So even though we're not accustomed to writing it down that way, that is what we know when we start out. And so this is just a simple cross. Without any extra information, we would say that the chance the individual is big A little a is 1/2. Okay, so then we the individual is born, we see their phenotype, and we see that they're unaffected. And so now we have the probability that the individual is big A little a, given that they have heterozygous parents and that they're unaffected. And so now we can write down all our probabilities, but we can cross out little a, and we're left with the probability that they are big A little a divided by the probability that they're unaffected. Okay, and so now this individual meets an individual who is carrying the trait, and they have an offspring. So let's say their first offspring is unaffected. Then how does that change things? Okay, so now what is A? Well, A is all the data we have, so everything we know. So now it's, let me just rewrite for 1 sec. Okay, and so now what we're asking is the probability of big A and little a, given that all this stuff and one unaffected offspring. One unaffected offspring, this offspring. Okay, so now what do we have to do? Well, we have to work through our probability. If this individual, if our focal individual, number 1, is big A, then what's the chance they'll have an unaffected offspring? Well, it's 1, right? So, unaffected offspring. If they're big A, little a, then there are two possibilities. They could have an unaffected offspring, or they could have an affected offspring. Affected offspring. Okay, so now what do we do? Well, okay, so in our pi method, well, this probability still stays as 1/4. So they're big A, and one unaffected offspring. We're just going to do UO for unaffected offspring. Over here, our probability distribution is going to get split in half because there are two possibilities, big A, little a, and one unaffected offspring, or big A, little a, and one affected offspring. Okay, but because we know that this individual had an unaffected offspring, we can erase stuff, right? So we can erase the affected offspring here, and we can erase this path down here. And so what we're left with, so this is 1/4, this is 1/4, and we get the probability that big A, that the number one is big A, little a, given that individual one has big A, little a parents, and is unaffected, and has one affected offspring, is equal to 1/4 divided by 1/4. Sorry, divided by 2/4. 1/4 divided by 2/4. 1/4 divided by 2/4. Okay, so then if that individual has another unaffected offspring, so now we'd say, now we're asking probability of big A, little a, given everything we knew before, and another unaffected offspring. So let's say, we'll just do UO, and a second unaffected offspring. So now B is still probability of big A, little a, but A is all our data. This whole, everything we know. Okay, so now what happens? Well, in our method here, we have our two paths that are still alive. If big A, if the individual is big A, then we expect a second unaffected offspring. So second unaffected offspring. If the individual, unaffected offspring, if the individual is big A, little a, now we again have a 1/2 chance of the second unaffected offspring, and we have a 1/2 chance that our second offspring is affected. A second offspring is affected, second AO. And then in our pi method, what this means is that this again splits in half, big A, little a, and one affected offspring. But the second offspring means that we could either have big A, little a, and two unaffected offspring, or big A, little a, and one unaffected offspring, the first one, and then a second offspring is affected. So we can just do that as U, comma A, unaffected offspring and then affected offspring. Okay, so which of these can we erase? Well, both offspring are unaffected, so that works here and it works here, but it does not work here, so we erase this one. And similarly with our path, it doesn't work here, so we erase this one. And so now we can calculate everything out, and we get that the chance big A, and two unaffected offspring is 1/4, and then now we're down to 1/8. And so now we can update our probabilities. So now we have probability the individual is big A, little a, and all the data, and we get 1/8 divided by 1/4 plus 1/8, which is 1/3. So you can see what's happening here. So before they had an offspring, the probability was 2/3. Then after they have the first offspring, the probability is 1/2, and now it's down to 1/3. So it was at 2/3, 1/2, 1/3. So the more we learn about this individual by observing their progeny, the more we know we can change our probabilities. So let's just do one more. So this would be if we have a third offspring that's unaffected. The probability of big A, little a, given all this stuff, and a third unaffected offspring. So again, this is going to, this big A piece is going to stay the same because it keeps being a probability of 1. And then this one, again, is going to fork. We have 2 possibilities. So we get third unaffected offspring, and we get third affected offspring. And so then, once again, we can get rid of this bottom path, and we get 1/4 for this path, and we get 1/16 for this path. And so this is again going to split in half. And so we have big A, little a, 3 unaffected offspring, and then we have big A, little a, unaffected offspring, and then an unaffected offspring, and then an affected offspring. And so again, we can erase this. We calculate this through, it's 1/16, and now we have 1/16 divided by 1/4 plus 1/16, and now we're down to a probability of 1/5. So it makes sense, right? The more times we observe that when this couple reproduces, they have unaffected offspring, the more we become confident that this individual must not carry a little a allele. If these individuals had 20 offspring and none of them were affected, then we become quite confident this individual does not have a little a allele because they keep not passing down a little a allele. They keep passing down a big A allele. And Bayes is the way that we can do this explicitly. So that's pretty much all I have to say, but let me just say one more thing, just to point out. So then what happens, so let's say we have a whole bunch of unaffected offspring, and then at the end, we have an affected offspring. So then what happens? Well, as we've said, this path, the path of a lot of unaffected offspring, keeps shrinking. And so the more offspring that we have, the littler this pie gets. But then what happens when we have an affected offspring? Well, as long as we leave aside weird things like recurrent, like a second mutation, a new mutation, well, suddenly this big piece of pie that we've been able to keep around the whole time gets erased. This whole path gets erased, and we're left with only one path. Big A, little a. So once we have data that rejects the big A hypothesis, because now this individual cannot be big A, then suddenly we become confident that despite all these unaffected offspring, this individual is big A, little a. Thanks.